for I equals 0, I less than n, I plus plus. Wouldn't it be convenient if there was a less verbose way of basically looping while incrementing a value by 1 each time? Seems like it's a pretty inefficient way of conveying that information. Anyway. Alright, so what would it look like? Well, integral equals to 0 at the beginning, and then you will add every time you will add a little bit. You will add something like this, right? F of something times the difference something. But actually, let's make a name for that. So double H. H is going to be the size of each subinterval. So it starts with B minus A, right? But you divide it so n is going to be the number of intervals. Right? So then you multiply by h. And then you start at A, because the first one will look something like this. You know, it's going to be A times, but instead of B, it's going to be A plus a tiny bit, A plus H. So we get that. And if you do I times H, right, double I times H, let's see if that works out. So you have 1,000 intervals, and you're doing this thing 1,000 times. So you're adding 1,000 things to this variable, and each one of these things that you're adding is f at a certain point. Okay, the first thing is going to be f at A, and the last thing is going to be f at A plus (999) times B minus A over 1,000. it's going to be b minus a, so 1,000 over 1,000, minus 1 over 1,000 times b minus a. It's going to be b minus a, so a plus b minus a, which means b, minus 1,000 times b minus a. And 1,000 times b minus a is just h. So it's going to be, the last thing is going to be b minus h. So for the last one, we're taking this value. This would be b, f at b, and this is f at the one before that. And then you multiply by this length, h. All right, let's give that a try. Remember, before that, the integral we came up with was equal to 0, which was bad. Does this do any better? So we see it's doing not terrible, but it's definitely better than 0. It's got the first 2 digits right, and the last digit isn't far off, right? Can we get it even better? Well, if you reduce the size of the interval, it should do the trick, right? So now I multiply the size of interval by 10, by 10 again, by 10 one more time. So 1, 2, 3, 4, 5, 6. We still have one digit that we can try. See, now it's taking time. It's no longer instantaneous. And it still doesn't work, right? That function, it's pretty bad. It's pretty steep if you just put rectangles beneath the function. They're always beneath. So takes a while. If you get 100 steps, see, 100 steps, it's worse than 1,000. But after 1,000, you don't see the difference, which is probably, so you have to notice that there's a cutoff when we print. Don't want to get into that right now, but yeah, there's a cutoff when we print, and it's possible that it's like 150,99999. We would still see only 150 because it stops printing after that. So 1,000 is okay. And so it's pretty imprecise, right? It's not super good. How do you make it better? Well, as it turns out, you can make it better simply by assuming that instead of having a constant, you have a linear function. So I, a to b, f of x dx. Suppose f of x is a linear function from a to b, right? Then the value of the interval is going to be f of x is equal to say kx, right? Which gives you k times x squared over 2 between a and b, so it gives you k times k times b squared over 2 minus a squared over 2. Right, which is not super good. So how do we do this? How do we do this? Well, if f is a, that's one way of doing it, but it's not very insightful. So another way we could think of this is we can say f is equal to f of a plus plus x times so right now this just have this how do you see this? Like, I know what the answer is, and should be pretty obvious. Okay, so it's actually better to emphasize that the interval is small by saying you integrate from a to a plus h. So I appear to be too tired to think on the spot, which is a bit sad, but so from a to a plus h, then what is okay, if we wanted to have